What are the first theorem? Every continuous function is integrable. Second function, a bounded function f which has only finite number of points of discontinuous in AB is integrable. See, first theorem is every continuous function is integrable. Suppose fx has only finite number of points of discontinuities. You know that what are discontinuities? Then also it is integrable. Now to prove this, what do you have to prove now? If the function has only finite number of discontinuities, then the oscillatory sum of f in that interval AB is also less than epsilon. If oscillatory sum is less than epsilon, you know that function is integrable. For that, suppose fx has finite number of points of discontinuities. Suppose fx has p number of points of discontinuities. Points of discontinuities. Now we enclose these p points of discontinuities in a non-overlapping intervals. What are that? A1 dash, A12 dash, A12 dash, A2 dash, A2 dash, A22 dash, so on, AP dash, AP2 dash. We enclose these p finite number of discontinuities in the non-overlapping intervals A1 dash, A12 dash, A2 dash, A22 dash, AP dash, AP2 dash, so that the corresponding oscillatory sum due to these intervals is less than epsilon by 2 into m minus m. See, this is important. We have enclosed these p points of discontinuities in the non-overlapping intervals, and also the oscillatory sum due to these subintervals, oscillatory sum of fx due to this subinterval is less than epsilon by 2 into m minus m. Now oscillatory sum due to these intervals, oscillatory sum is less than epsilon by 2 into m minus m into m minus m. M minus m is oscillation of fx. Therefore, oscillatory sum arising from these subintervals is equal to epsilon by 2. This is first one. So we have enclosed that p points of discontinuities in non-overlapping subintervals, so that the oscillatory sum corresponding to that division, that intervals, is less than epsilon by 2. Now in the remaining subintervals, that is A1 dash, A12 dash, A2 dash, etc., AP2 dash, B. These are the remaining subintervals. How many subintervals are there? P plus 1 subintervals. Fx is continuous because we have enclosed the discontinuities in P subintervals. In the remaining P plus 1 subintervals, Fx is continuous. Now using that first theorem, we can divide this subintervals again into number of subintervals, so that the oscillatory sum corresponding to these subintervals, or oscillation of fx in each of these subintervals is less than epsilon by 2 into p plus 1. Fx is continuous in p plus 1 subintervals, and we can divide these subintervals in such a manner that the oscillation of fx in each of the subinterval is less than epsilon by 2 into p plus 1. Then the contribution to oscillatory sum by these subintervals, these p plus subintervals, is less than epsilon by 2 into p plus 1 into number of subintervals p plus 1 is again epsilon by 2. Now from 1 and 2, the oscillatory sum of fx due to that division d, that is omega d, is less than epsilon by 2 plus epsilon by 2. Hence oscillatory sum is less than epsilon. So fx is integrable. Fx is integrable. Hence, if a function has only finite number of points of discontinuities, then also it is integrable. The art of writing the proof is important. In the first part, we have enclosed that p finite number of, we have assumed that there are p number of discontinuities, and we have enclosed that p number of subintervals in a1, a1, a1 dash, a1 2 dash, a2 dash, a2 2 dash, and so on, p subintervals, so that the corresponding oscillatory sum due to that subintervals is less than epsilon by 2. And the remaining p plus 1 subintervals, function was continuous. Since it was continuous, we can have the oscillatory sum corresponding to that subintervals as again less than epsilon by 2. What is the total oscillatory sum? Epsilon by 2 plus epsilon by 2 less than epsilon by sufficient condition of integrability. Since the oscillatory sum is less than epsilon, fx is integrable. So two theorems are over, and the third theorem is like this: every monotonic function is integrable. Every monotonic function is integrable. Third theorem. Every monotonic function is integrable. Now this is third one. Another theorem is left on classes of continuous functions. Proof of that two theorems I explained in next video. We will go through these videos, and as I told earlier, if you have any difficulties, if you have not followed any points, you can ask at any time. Okay, thank you.